Welcome to This Explainer. Today, we're literally opening the hood on what I think is absolutely the most thrilling area of artificial intelligence right now, the architectures of reinforcement learning. If you've ever wondered how machines are evolving from just, analyzing static data to actually making complex split-second decisions in the real world, well, let's figure it out together. Okay, let's dive right into this. How exactly does a machine learn to navigate a super busy city street or completely outsmart human grandmasters at games we've played for centuries? I mean, a human programmer didn't sit down and code every single possible scenario, right? There's no way. The machine taught itself. And understanding exactly how it pulls that off is what we're going to unpack today. So here's our game plan. First, we'll officially meet reinforcement learning. Then we'll look at the core RL loop, followed by a deep dive into 6 key algorithms. Finally, we'll explore real-world AI successes and wrap up with the challenges and the future of this tech. Let's get to it. Section 1. Meet reinforcement learning. Learning through experience. Now, you might already be pretty familiar with supervised learning, where we hand an AI a bunch of labeled data. But reinforcement learning, or RL, is an entirely different beast. In RL, an agent learns by interacting directly with an environment. It has one simple yet incredibly powerful objective: maximize rewards and minimize penalties. That's it. There's no answer key provided. It's purely learning through trial and error. So the crucial point is, well, to intuitively understand RL, just think about training a puppy. You ask it to sit, that's the action. If it actually sits, it gets a treat, a positive reward. If it just barks at you, it gets nothing. Over time, it figures out the winning strategy. We can map this exact same logic directly to AI. The algorithm is the agent, its decision is the action, and the mathematical feedback it gets is the reward. It's the exact same concept, just applied to code. Section 2. The core RL loop, the cycle of decision-making. Let's move to and see how this builds, because this learning process isn't a one-off event. It's a rapid-fire continuous sequence. First, the agent observes its current state, say a self-driving car algorithm seeing a red light up ahead. It selects an action, like braking, and then actually performs it. Next, it receives a reward, which in this case would be a massive positive score for, not crashing. It then moves to its new state, stopped safely at the intersection, learns from that successful outcome, and repeats the whole process. This continuous loop is literally the heartbeat of all RL. Section 3. 6 key RL algorithms, escalating the complexity. As these environments escalate from, say, simple digital grids to chaotic real-world streets, the algorithms have to get much, much smarter. First up in our toolkit is Q-learning. Imagine a tiny robot dropped into a simple maze. Q-learning basically builds a giant spreadsheet called a Q-table. For every single spot in the maze and every possible move it can make, it records a score based on its past experiences. So it consults the table, picks the highest score, and eventually learns the absolute shortest path. It's a brilliant approach, but as you can imagine, physically limited by memory. Now, what's really interesting about this comparison is the scale. A Q-table is great for a small maze, for sure. But what if the agent is playing a highly complex video game? You literally can't build a table for every possible combination of pixels on a screen. The universe just isn't big enough to store that amount of data. That's where the Deep Q network, or DQN, comes to the rescue. Instead of relying on a rigid, memory-heavy table, it uses a deep learning neural network to predict the best action directly from looking at raw screen pixels. This lets it handle millions of states dynamically. It was a real game changer. Next up is SARSA. This stands for State, Action, Reward, State, Action. While Q-learning might boldly assume the agent will always take the most optimal path in the future, SARSA is a bit more grounded. It updates its knowledge based on the actual actions it ends up taking, even if they turn out to be mistakes. Think about a self-driving car algorithm in training. You definitely don't want it being overly aggressive or taking crazy risks. SARSA results in much safer, more cautious, conservative learning. And that's absolutely critical for systems where a failure means a physical crash rather than just a game over screen. Algorithm number 4 kind of changes the paradigm completely. Instead of obsessively scoring every single possible action, policy gradient algorithms skip the middleman and directly learn the overall strategy, or the policy. Imagine a bipedal robot trying to learn how to walk. Calculating the exact mathematical value of twisting a knee joint by 1.2 degrees versus 1.3 degrees, that's a total mess. Instead, policy gradients gently tweak the overall probabilities of its movements. Basically, it just smoothly learns to fall over less and walk more. Building on that idea, we get actor-critic algorithms. This essentially splits the AI's brain into two distinct neural networks working together. You have the actor, who is out there in the environment making decisions and choosing actions. Then you have the critic, who stands on the sidelines evaluating those actions based on the rewards received. This dedicated coaching dynamic makes the learning drastically faster and way more stable. It's pretty much perfect for highly complex industrial automation and advanced robotics. Finally, we reach proximal policy optimization, or PPO. This is widely considered the current industry standard. See, a major problem in AI training is that an agent can suddenly just forget how to do a task entirely if it drastically overcorrects its strategy after one weird mistake. PPO solves this by putting strict mathematical guardrails on the learning process, effectively preventing those sudden, destabilizing changes. It perfectly balances high performance with stability, making it the absolute go-to choice for the most advanced simulation environments running today. So just take a second to look at how far we've come here. We escalated from the simple tabular memory of Q-learning, pushed through the neural network power of DQN, added the caution of SARSA, achieved the smooth, continuous control of policy gradients, harnessed the dual network brilliance of Actor-Critic, all the way to the stable, highly tuned optimization of PPO. Seeing this progression laid out really helps us understand exactly how engineers pick the right tool for the job. Section 4. Real-world AI successes, from games to the grid.
And this brilliantly illustrates what happens when we unleash these algorithms on the real world. The results are historically disruptive. When Google DeepMind built AlphaGo, it didn't just play the ancient game of Go. It completely defeated human world champions using moves we had literally never even conceptualized before. Today, RL is out there powering split-second decision-making in autonomous vehicles, allowing robotic arms to skillfully manipulate fragile objects they've never encountered, and even mastering incredibly complex cooperative multiplayer video games like Dota 2. It's wild stuff.
Section 5. Challenges and the future. What lies ahead? But, as miraculous as these achievements absolutely are, there are some very grounded realities and bottlenecks we have to talk about. First, long training times. We're talking millions upon millions of interactions just to learn basic tasks. Second, astronomical computational costs that require massive, power-hungry GPU server farms. Third, the incredibly delicate mathematical tightrope of balancing exploration against exploitation. And finally, unpredictable reward design. If you tell an AI to simply make a paperclip without setting careful boundaries, well, it might just consume all the universe's resources to maximize its output. Yet, despite those bottlenecks, the horizon is incredibly bright. By fusing reinforcement learning with deep learning, we're looking at machines that can adapt to the unknown completely on the fly. We're talking space exploration robots that repair themselves on Mars without having to wait for Earth's instructions, smart factories optimizing complex global supply chains in real time, even personalized healthcare systems that dynamically adjust your treatments based on your immediate real-time biological feedback. We've covered the architectures, the massive successes, and the real-world hurdles, but I want to leave you with this to consider. If we are rapidly perfecting algorithms that allow machines to learn virtually anything through trial and error at speeds millions of times faster than humanly possible, what limits actually remain for fully autonomous systems? Thank you so much for joining me for this explainer. Keep asking questions and keep learning.